All right, welcome back. This video is about periodic trends, which are giving us the ability to use the periodic table to predict properties of atoms. Now, these are often, not always, so the only way you can truly know the actual property of the element would be by doing an experiment and to compare two atoms. So this is often, not always. It's a really useful tool, but you can't take it necessarily to the bank. The first trend we're going to discuss is called activity. Now, for activity, it works like this. There's two regions that you need to focus on the periodic table. You need to focus up by fluorine and then also down by francium. As you move down into the left of the periodic table, the atoms, the metals, become more active. So down families, atoms become more reactive, or from right to left across the period, atoms become more reactive. So if you're comparing two atoms that are right next to each other vertically, the one further down for metals, or the one further left for metals. Then on the other hand, nonmetals, as you move up a family or you move right across a row or a period or a series, that atom becomes more reactive. Fluorine's the most reactive of all the elements, and then the noble gases are unreactive. They don't really readily form compounds. The atomic radius, so that's the distance across an atom divided in half. So from the center out to the outside, that's the atomic radius. And our trend looks like this. Small atoms are up and to the right. So focusing towards helium, notice that we're not including the noble gases as they're not important here. They are important. So smaller up to the right, and then bigger down to the left. However, hydrogen is the smallest atom because it's just a proton and an electron. The factors that come into play here, the more important of the two, is the number of energy levels. So as you go down the periodic table, you go from energy level 1 to energy level 4, you have basically 3 additional layers of clothes on going down that family. And each layer adds a distance to the radius of that atom. The second factor, this is less important than the number of energy levels here. As you go from left to right, the atoms get smaller, and that's because for a given energy level, so a given distance away from the nucleus here, we are adding more electrons, so they're not getting added any further out to the from the nucleus. But as we go right, we're adding more protons for each electron. So each proton has a larger pull on that electron. So it's kind of like a vacuum cleaner. Out here on the left-hand side of energy level 4, for example, I put my first electron in energy level 4, and I add one additional proton. Now as I move across, I'm putting more electrons in energy level 4, so they're not getting any further away from the nucleus, but my positive pull is going to get greater. And since opposites attract, the power of my nucleus is like the power of a vacuum cleaner: weak vacuum, strong vacuum. As far as the energy levels here, I like to think of, from the Christmas story, Ralphie's little brother, I think it's Mikey, as he gets more and more layers, he gets bigger and bigger and bigger. So more layers of clothes, bigger atoms. Now, ionization energy, first need to know kind of what that is. It's the amount of energy needed to remove an electron from a neutral atom. And as you take more electrons away, once you take one electron away, of course the energy gets greater and greater and greater to take those additional electrons away. If your value happens to be a low number, it's easy to take that electron away. On the other hand, if you have a high ionization energy, it's hard to take electrons away. Now, atoms that are big down here on the left, they give away their electrons really easily. They're kind of just letting them hang out. On the other hand, these are atoms that are really, really small, so they're holding on to their electrons very tightly. I like to think of it as maybe a woman walking with a purse. Depending on where you are, if you're walking through a neighborhood that you feel safe in, you might just let your purse hang out in the breeze and it'd be really easy to snatch it. On the other hand, if you're walking in a neighborhood that you might be a little bit more concerned about, you're going to hold on to your purse really, really well. Or a football example would be high and tight. If you're holding on to the football high and tight, you're not going to be able to give away that football. It's going to take a defender a lot of energy to strip that football. On the other hand, if you're not carrying the football high and tight, it's really easy to strip the football. Shielding effect is in play here. As you go down the family, there are more and more rows of, or more and more energy levels of electrons. So the inner energy level of electrons start to block the outer energy level of electrons. And what happens is the nucleus doesn't have as much effect on the outer energy levels of electrons because the inner energy level of electrons are shielding those outer electrons. This is also true for noble gases. Noble gases have very high ionization energy because they already have a stable octet of electrons, and they don't want to give up any electrons, so they're going to really hold on to those electrons tightly. Ionization energy is kind of related to electron affinity and electronegativity. Ionization energy was removing electrons. This is just looking at how much atoms like electrons. Now, electron affinity is you look at an individual atom and you measure how much does it like electrons. How well does it share electrons, kind of. Electronegativity is how much does it share electrons in a given bond. So you compare two atoms bonded to each other and how well those atoms share is the electronegativity. If you're not very good at sharing, you have high electronegativity. If you really want to always have that electron, you have high electronegativity. And then on the other hand, if your electronegativity is low, you're okay with the other person always having the electrons. Low attraction, so this is low electron affinity, low electronegativity. Fluorine has the highest electronegativity here. These atoms here, the noble gases, so this is different than ionization energy, have zero affinity for electrons. Noble gases don't want them at all. And again, the shielding effect is coming into play. Density, so this is a pinching trend, different than the other trends that we've already looked at. As you go towards the middle of the periodic table and as you go down the periodic table, the values get higher. So the key for density is to focus on the two highest ones. You have iridium and osmium. Now specifically this column, cobalt, rhodium, iridium, have the highest values. So as you pinch towards these, the values get higher. And then iridium and osmium have the highest. They're neighbors next to each other. Osmium would be right here. So 22.6 is the highest density, and as you go down the families, it gets larger. As you go towards the middle, towards these atoms, they get higher. Now, if in doubt, if you're not sure exactly which is going to be a more dense atom, use the one that has the higher atomic weight. And then finally, melting point and boiling point. These again are both pinching trends. Now this is a little different. As you go in towards the middle, again, the values are going to get higher. So for melting point, they'll focus on tungsten. Tungsten's the highest. Chromium and molybdenum are also high. So as you go down the family, they're the highest, but tungsten's the highest of them all. And the difference, though, here between density and melting point, boiling point, for families 1 and 2, as you go up, the melting point or boiling point actually increases. So going up these families, the melting point, boiling point increases. But then the rest of the table, as you go down, the melting point, boiling point increase. So after looking at this, you should have learned about 6 different periodic trends, and you should know that these are trends. They're not always, they're often. The best bet is to record these rectangles and draw some arrows, and that'll help you study. Hope that helps.